All right, guys, here we go. So there it is. Uh, we're kind of we're jumping around a little bit on this one exactly because just kind of showing you where we're going to head towards things, and we've got some good review in the derivatives. So I've got a new program. Well, it's not new; it's Cami, but it's better than that one that started flashing. But I don't like it because it's got this big zero arrow that does that. That's irritating. But we'll see what I can deal with here. So here's the idea. Parametric equations are uh, equations that have an independent variable in them that relate them both. So it has an independent dependent variable. Probably spelled dependent wrong. Independent variable that relates them both. And it's usually time. So it's usually time. So you'll see it like down here. Look, it's t for time. That's the idea. It's t for time. So we're going to be doing, typical acceleration stuff with this and speed and first and second derivative stuff. But here's the idea. So where to graph on your calculator? You got to graph these different on your calculator. So in your calculator, you need to go to mode. And when you want to graph these things, you change them over to the mode. You got to go parametric. So we got to go back and forth if we need to on this. So mode is parametric. And then when you go to parametric, it's going to give you like two equations. It's going to give your y equation and your x equation. I can't remember what it looks like, and I don't have my calculator in front of me. But you're going to get two equations to plug in before you can hit graph. You'll hit graph like normally, but you just got to go into the parametric mode. So you click in mode, do parametric, you plug in your equations, and you go from there. So here's the idea. So we can graph them, and I'll show you this one. So, and it kind of this is going to pop up here too, but there's a couple of different things we can kind of do. So I'm going to tackle two birds with one stone. So you have the parametric plane, which is going to have t as your independent variable on the bottom, and your dependent variables are on the top. Or it's the Cartesian plane. So if we look at this, so let's just let me just draw this out. So here we go. Here's my x. My x is the square root of t, which can change. And my y is t, right? That's my variable. So if I put in 4, for t, if I put in 4 for t, that means, let me say t equals 4. That means that I'm at 2 and 2. You guys okay with that? So 2 and 4. So I'm at 2 and 4. 1, 2, 3, 4. And if I put in t equals 1, this is my independent variable that's changing. If t equals 1, y is 1, and t is 1. So put 1 here, and I got that one. If t is equal to 9, square root of t is 3, and y is 9, so it's way up here, like this. So I start getting, and if I put in 0, t is greater than or equal to 0, so I can put in 0, and I'm going to get 0. So now all of a sudden, I get this graph that kind of looks like a half of parabola. So this is my parametric equation. I have two functions, x equals square root of t and y equals t, representing the y-axis, and my independent variable changes, so I have two values that get popped out, and that's my parametric equation. But what does that look like on the Cartesian plane? So I'm not very good at erasing yet, guys, so you guys are like, great, here we go. Bad memories, nightmares, whatever it was when I first started learning how to do these. So let's look at this deal right here. So let's just look at this right here. This is fun, amazingly fun. So I can relate these two by solving. So let's just say I can find t. I'm going to use this one for instance. I know that x equals the square root of t. Therefore, I know that t is equal to x squared. If I know that t is equal to x squared, I can plug in t to that equation. So then I know that y equals x squared. So y's got to equal x squared. Well, y equals x squared, and that's my Cartesian plane. Cartesian plane is just your x and y's. It's your x and y axis. So on a Cartesian plane, this is actually a parabola, which is this half right here. Okay? So we can relate them to Cartesian planes, but I needed it because we can't have a value of 0 under there, so we didn't use this half right there. So that's how we deal with them graphing by hand or making them on a Cartesian plane. So for a Cartesian plane, you're going to solve for t and then plug t back in. It's usually easier to use the x value and you work for there. So that's finding the Cartesian equations. So this here, so if we look at x equals the square root of t and y equals t, the Cartesian equation is y equals x squared because x squared equals t, and I know that t can be plugged in there, and that's how I get my Cartesian equation, okay? So the other thing happens is when we're dealing with trig functions. Trig functions are a little different, so let's just take the first one here, and we look at let's see here. When you're dealing with trig functions, you're always dealing with when you're moving them from Cartesian to parametric. So let's just start with this one. X equals cosine of t, and then y equals sine of t. Okay, when you're dealing with this, remember, these are a unit circle piece. So to find the point, we're actually dealing with x squared plus y squared, right? Because we're dealing with the unit circle. So we got this unit circle piece here. And the fundamental piece of the unit circle is this triangle here, right? And if we're dealing with this triangle here, how do I relate this unit circle or this triangle to the Cartesian plane? Well, I have cosine here, and I have sine here. And I know that this is 1, right? Well, how do I relate this x value and this y value to the unit circle of 1? Well, I know that cosine squared plus sine squared equals 1. So therefore, if I can turn cosine and sine into values, then I can use this identity at cosine squared plus sine squared equals 1 to find my Cartesian. And lo and behold, what is cosine of t equal to? Cosine of t is equal to x. And then what's sine of t equal to? It's equal to y. And so my equation is a basic circle. Makes sense because cosine and sine relate the circle to trig functions. And so therefore, if I'm given a trig function, I can turn around and relate it back to a circle. So it gets a little trickier at times. So let's look at another one, which is x equals 3 cosine of t and y equals 2 sine of t. So let's turn this into a Cartesian plane. So we know that if I divide by 3, I get cosine of t, x over 3, and sine of t, Whoa, that was crazy. Sine of t is equal to y over 2. So now I can use my handy dandy little idea where I know that this is x over 3 squared plus y over 2 squared equals 1. And since they're different distances and different values, it's more of an elliptical shape. And if you plug that into your calculator, uh, it would do an ellipse for you, or into Desmos, it would do an ellipse. So we can relate these back to the Cartesian plane using the fundamental identity of cosine squared plus sine squared. So that's just a quick intro to parametric equations, and we will tackle derivatives of these bad boys.